Okay, so those were the homework questions. Let's do them quickly. So this was 2003 examen final. Number 4, the 2-3 spinel. MGTO 204 is a normal spinel, and a normal 2-3 spinel. So these are on the octahedral sublattice, and this is on the tetrahedral sublattice, octahedral sublattice. MG2TI4 is a 2-4 spinel with magnesium on this sublattice and magnesium and titanium randomly distributed on the second sublattice. So you see, first of all, it is actually just a one sublattice model. The first sublattice is always occupied by magnesium, so it's really just the one sublattice where any mixing is going on. So we're supposed to talk about a model and write an expression for the Gibbs energy. Okay, so we write it out as magnesium on this sublattice, and then magnesium, titanium 4, and titanium 3 all mix on this sublattice with a total of 1 minus x, 1 plus x, and 2x is 2. So there are 2 sites on this lattice. So it's a simple one sublattice model. If you want to treat it as just a simple ideal mixing solution, this would be the ideal mixing activities. The activity of MgTI204 is simply the mole fraction of it's just like we use it for any sublattice model. It's the mole fraction of magnesium on this lattice times the site fraction of titanium on the second sublattice squared. This is titanium 3 plus. So the site fraction of magnesium on the first lattice is 1. The site fraction of titanium 3 plus on the second lattice is 2x divided by the total, which is 2 squared, which would be x squared, or x of Ti3 plus on the V lattice squared. So that would be your ideal activity of MgTI204 if you would just have the ideal mixing term. And the activity of Mg2Ti4, this is Mg2 plus, this is titanium 4 plus. Once again, the magnesium 2 plus is on this lattice, the titanium 4 plus is on this lattice, and so you have 1 minus x divided by 2 squared. Sorry, 1 minus x divided by 2. No, not squared. Sorry. What I messed up here? No, that's not right. Sorry, what? Oh yeah, sorry. Yeah. Okay. This is Mg2. This is Mg2Ti04. So this is Mg Ti4 plus 04. Okay, so it's the product of the site fraction. Okay, so the magnesium on this lattice is 1. On this lattice, the fraction of magnesium on this lattice is 1 minus x over 2, and the fraction of titanium in that lattice is 1 minus x over 2, titanium 4 plus. But you have to divide by the value for pure Mg2Ti04, because this would be, now you want the activity of pure Mg2Ti04, that is with no Ti3 plus on this lattice, to be 1. Okay, now even when you have pure Mg2Ti04, when you have only this, okay, by this formula, it's 1/2 times 1/2. So the only way to make this activity equal to 1 when you have no titanium 3 plus is to put a 1/2. This is equal, when x is 0, this is 1/2 and 1/2. So this is the activity of Mg2Ti04. Does everybody get that? No? Okay, your system is going from Mg/Ti3 plus 204 to, these are your 2 components. Those are the 2 components in the system. Okay, so you're going from pure Mg/Ti204 to pure Mg2Ti04. When you have pure Mg2Ti, when you have pure this component here, when there's no titanium 3 plus, its activity has to be 1 by definition. Okay, but if you take it to be this expression, even when x is 0, this would be 1/2, 1/2. Okay, x is the amount of what? X is the amount of this. This is x. Here you have x equals 1, here you have x equals 0. Okay, so when x equals, this is the activity, this would be the activity, the product of this composition times this, the fraction of Mg2 plus times the fraction of titanium 4 plus is 1 minus x over 2 times 1 minus x over 2. But when x is 0, when you're over here, you've still got 1/2 times 1/2. Okay, so you've got to divide by the value in the standard state in order to make it. This is your activity, this is your standard state activity, if you like. Okay, so that would have, that's how you end up with the activity of the MgTi2O4. Okay, because even in the pure material, you have a random mixture of these two things. If you make it 1/2, 1/2, you're going to end up with the pure material with an activity of 1/4, which isn't right. Okay, so if you want to get your standard state right, you've got to do it that way. I put this up on the server the other day. If you want to write a compound energy formalism model, we actually have three N members then. Okay, you have your 3 N members of magnesium, 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 titanium 4, magnesium, titanium 3. Okay, so your 3 N members are Mg, 3 plus 2O4, that's the real MgTi2O4. Here you have a fictitious N member, MgTi4 plus 2O4, that has a charge of 2 plus. This one has only magnesium 2 plus here, so that has a charge of 2 minus. And your real Mg2TiO4 is halfway in between. Okay, so this is your neutral line. So the actual material between these, the actual binary system follows the neutral line. Okay, but if you're writing this up as a compound energy formalism, you do it this way. Okay, I've called these 1, 2, and 3. So G then is the number of moles of 1 times G naught 1 and G naught 2 plus. Then you're mixing these three things, these 3 ions, you're mixing these 3 ions on the second sublattice. So there's 2 sites on the sublattice, so it's 2 RT. Since I'm doing this as the extensive property, is the total number of moles times x1 log x1 plus x2 log x2. 2 times that, right? So it would be total numbers. So the mole fraction of this is 2x over 2. Sorry, this should be sorry, there should be 2 times here because you're mixing all 3. Okay, there should be this plus another second term because you got 3 ions on this one. Okay, where N2, the number of 2 plus the number of 3 is actually the number of moles over 2. The number of moles of this plus the number of moles of this divided by 2 is the number of moles of your actual N member. Okay, and the Gibbs energy of real Mg2TiO4 is 1/2 the Gibbs energy of this plus 1/2 the Gibbs energy of this. Plus, now remember, even your real N member, you have an ideal mixture of these two things. So you've got even your real N member then is G naught 2 plus G naught 3 over 2 plus your mixing term, which is 2 RT, 1/2 log 1/2 plus 1/2 log 1/2. Okay. Okay, so if you were setting this up in your compound energy model, what you would have is you would have the G naught of this material. You'd have the G naught of this, that's your G naught 1. You have your G naught of this N member. Okay, so that if you're trying to, so you could set G naught 2 or G naught, Jesus Christ. Oh, I make these mistakes. This should be G naught 3, excuse me. That's G naught, this should be G naught 3, not G naught. G naught 2 plus G naught 3, and this term should have another term, 1 minus x over. Anyway, here you get G naught 2 plus G naught 3. One of G naught 2 and G naught 3 could be set arbitrarily to whatever you want. 0 and the other one then, because you don't, they're hypothetical, so one of them can have any value, or you can set them equal if you want. It's probably the best thing to do. Set G naught 2 equal to G naught 3, put this in, and then this is your Gibbs energy of the Mg2TiO4, which has been measured, and that would then fix your N member 2 knots. The important thing here is that a real N member, this is not an N member, it's the real material, and it can contain a non-zero configurational entropy. Your N members don't have. Any questions about setting that up? And you see how the entire compound energy formalism all sorts of things can be brought into it, but you do have to be careful. It's too much. You got to understand what you're doing. Okay, so sorry for the, I don't know, put a 2 in front of this and make that G naught 3. Okay. The important thing here is understanding this, why that's there. The G naught of the real Mg2 TiO4 is this plus this over 2 plus the mixing 2, which of course is related to why you got to put this in the denominator up here. So that? Alright, 2005, 2, 3. It's not it, what? 2, 5. Alright. Compounds, Fe2SiO4 and Mg2SiO4 with the olivine crystal structure, miscible at all compositions. There are 2 crystallographic sites. There's the Chem1 sites and the M2 sites, which are crystallographically different. Silicon and oxygen stay on their sites, so there's actually 4 sublattices, but these sublattices remain unchanged. And the iron and magnesium can go on both sublattices, which are crystallographically different. So I write an expression for the Gibbs energy, propose a set of model parameters which have physical significance, relate the formalism parameters to the modelism parameters, and if you didn't know anything but the Gibbs energies of the pure N members, or these 2 real materials, how would you estimate the formalism parameters? Suppose I lost that. Okay. Okay, so we set it up this way with iron and magnesium 2 plus on both sides. So SiO4. So here you've got your iron and magnesium FeMg, here's MgFe. These are not the same thing because the 2 crystallographic sites are different. Okay, so this Gibbs energy of this is not the same as the Gibbs energy of that, because this is a different environment for this site as this site. This is the pure Fe2SiO4, this is your pure Mg2SiO4 over here. Okay, and so we will say X and Y are the site fractions going this way. And I've called these 1, 2, 3, and 4 the N members. So G naught 1, 2, 3, and 4 are the Gibbs energy of the N members times X, Y, whatever. And this is mixing on the first sublattice, and that's mixing on the second sublattice. Okay, so first of all, G naught 3 is the Gibbs energy of real Mg2SiO4, which you can find in the books. G naught 2 is the real Gibbs energy of Fe2SiO4, which is actually a metastable. Well, no, you can find it. Okay, fail that. Okay, then what is, so you have these two formalism parameters are actually real parameters. You got 2 others here. These are not real compounds. They're neutral, by the way, but they're not real compounds. So you have your exchange Gibbs energy, which is 4 plus 1 minus 3 plus 2. So 4 plus 1 minus 3 plus 2 is in nearly any reciprocal system, is the exchange Gibbs energy, which is really your model parameter. Okay, the model parameter then is related, what does it physically mean? It's related to the relative, these things are, let's go to the old-fashioned way, this thing never breaks down. They're related to the relative preference of iron for the M1 and M2 sites. Okay, the M1 and M2 sites have different energies on them, and basically the iron prefers one site and the magnesium prefers the other site. Okay, so one of these, this 1 or 4 is going to be favored over the other. So the actual, if you go from, this is your pure Mg2SiO4, this is your pure Fe2SiO4, as you go through the system at internal equilibrium, you're not, if these 2 had exactly the same energies, if the 2 sites had the same energies, then your composition path would be a straight line along the diagonal. With these things simply, your real composition path would be the diagonal here, where say the number of these and the number of these was equal. The magnesium and the iron simply distributed themselves randomly. Okay, but in actual fact, you're either going to curve around this way, or you're going to curve around this way. It's going to tend to, there's only going to be one line through here, but the actual line's either going to go this way or going to go over that way, depending on which sites are preferred. Okay. And that's basically then what this model parameter is going to tell you. If the model parameter becomes greater or less than. No, that's wrong. I wrote this up, all these things in haste yesterday. That's not right. This only depends on the sum here. So it doesn't really matter, does it? No matter what this is, no matter what your exchange energy is, you're going to go along the same path, right? Or not. If that exchange gives energy becomes greater or less, what's going to happen is it becomes greater or less, you're going to end up with these things wanting to mix or not wanting to mix. So what? I would say the most important thing is G01 and G04, the difference between G01 and G04, which is going to decide on whether it's going to want to go this way or it's going to want to go that way. If G01 is more negative than G04, it's going to want to put the iron here and the magnesium here as much as it can. If G04 is more negative, it's going to want to put the iron and magnesium this way around as much as it can. Okay, so G0, this I'm out to lunch here, G01 minus G04, as far as I can see, is going to be the criterion here. Or is it? If the exchange gives energy, is going to tell you a probability of, it's going to give you a miscibility gap, a tendency to immiscibility on here. Magnesium tend to prefer to be nearest neighbors and the two irons prefer to be nearest neighbors and they don't want to go the other way around, then this will be negative and you'll tend to have, these will be a stable pair and you'll tend to have a miscibility gap here.
This would make that you don't follow the straight line?
No, you'd follow the straight line. In my mind now there are actually two. I do believe this is a model parameter. This is a model parameter. Okay, this model parameter is going to determine whether this is the stable pair or this is the stable pair, whether these actually prefer to. Okay, but there's going to be another model parameter, which is 1 minus 4, which is going to determine which way you want to go along here. So you're really going to have two model parameters. Not just, you have the two, you don't have, you can't choose one of these arbitrarily. All four formalism parameters have a meaning. But the this thing and the difference between G4 and G1 are actually two model parameters that are the things that actually physically determine what's going on. So if you make this more negative than this, it'll tend to go this way. If you make this more negative than this, it'll tend to go this way. But at the same time, this sum here is going to tend to give you a tendency to demixing or not. So that's the effect you were going to get if you. Okay, so you have both of these formalism parameters are important. You can't, as in the previous, well, when you have, like in the previous example, when you have truly hypothetical things, one, what your charge, there's always going to be at least one which is arbitrary. They can't all be meaningful. But in this case, they all are neutral. They all could have physical meaning. So it's not just the differences. So as you see, it's easy to get confused with these things, even when you.
Would it have been possible to use this model, but for the first number?
Well, the first example just had one sublattice mixing. Well, this has two sublattices.
But would it be possible to use two sublattices, like Mg2 plus mix with Ti3 plus?
In the first example?
Yeah.
No, because there really is only one sublattice. Mg2 plus, Ti3 plus, and Ti4 plus mix on the same crystallographic sublattice. Here you have two distinctly different crystallographic sublattices. If you don't know anything except the Gibbs energies of the two end members, then you've got to assume it's an ideal solution. I mean, the two real. If all you had was the Gibbs energy of this and the Gibbs energy of this, and you have no information whatsoever on the phase equilibria or on the site distribution, then you would just have to assume that G01 was equal to G04, that this was equal to this, because you have no idea otherwise, and also you'd have to assume that the exchange Gibbs energy was 0. So you have to set the exchange Gibbs energy to 0. If you wanted to make it an ideal solution of Fe2 and Mg2SiO4, and that's all you knew, then you would set this exchange energy to 0, and you'd set 4 equal to 1. It would just give you an ideal solution. Let's drop, well, I'm still on this here, so this makes it less moving around in these PowerPoints. Let's do the last one, 2003-21. This is always a good question for final exams. Number 1, no answers for this. For each of the following solutions, and one or two sentences for your grandmother, Chris Bale's grandmother, propose a structural model. Okay, not a whole lot of mathematics, just what's in the melt, what's there. Okay, so okay, got hafnium tetrachloride. Hafnium, by the way, is in the same group of the periodic table as zirconium, and rubidium chloride, which is an alkali chloride, and you got more rubidium chloride. So how would you model? What would you say that was? What model would we propose for that solution? Use our nice formalism here. How would you do that? I would say we talked about complex ions. So we have two sublattices. What goes on the first sublattice? Rb plus, and on the second sublattice? HFCl6, 2 minus, and chlorine. Silver bromide, which is just a little bit off stoichiometry towards the silver side. Actually, I guess I didn't talk too much about that, but does anybody know what the majority defects are? That's a defect model. The defect basically is silver ions go as in interstitials in that case. So you'd have silver on the silver sites, bromine on the bromine sites, and the excess silver would be in the interstitial plaques. Iron, manganese, and carbon solid. How many sublattices? 2. Okay, iron and manganese on the metal sites, carbon and vacancies on the interstitial sites. Germanium oxide and 90% calcium oxide in the liquid state. Simple model. Germanium is like silicon at first. Very, very basic. So your cation sublattices. Calcium, and over here you got GeO4s and oxygens. Now here your 90% boron oxide and 10% calcium oxide. It's a glass, which we consider to be more or less like a supercool liquid. Okay, so your boron oxide, well, I'm going to talk about that later today, but it is, as you know, like a silicate network. More complex, but you do have boron, oxygen, boron bridges, just as you do in silica. So you have a borate. B2O3 pure is like SiO2. You have your silicate SiO2, you have your silicate network where every two silicons are bridged through an oxygen bridge with the covalent bonds. Okay, then when you add calcium ions, it's the same thing. You add CaO, it'll break the bridge. So it's the same thing. So you'd have a 90% boron. You're going to have a borate network, a B2O3 connected network, with some of the bonds broken because you've added the network modifier CaO. The reaction being the CaO provides an oxygen ion plus then the boron oxygen boron bridge, and this breaks the bridge to form B2O-. Or it's the same thing as before. You can talk about an O2 minus, which is the oxygen ion coming from the calcium, plus an O0, which is the original oxygen bridge, forms two broken bridges. The network modifying reaction, the acid-base reaction. Why do they call boron oxide and silicon oxide acid, and why do we call calcium oxide a base? Because in the old, this is going back to the old aqueous chemistry notation and terminology, a base is an electron donor and oxygen is an electron acceptor. So basically they're saying that the calcium oxide donates a negative electron and is an electron donor, and the O0 here, the silica, the boron oxide, is an electron acceptor. Doesn't really mean anything, but that's the origin. Why we should say that. There's nothing to do with acid bases in aqueous chemistry, but that's the origin of the term going back 70 years or so. 1% PbCl2 and NaCl solid. And then we have 1% PbCl2 and NaCl liquid. Okay, well, an NaCl liquid, it's fairly simple. Let's do the liquid first. And the liquid, what you've got. In PbCl2, you have very few complexes. Lead is so big that it doesn't form complex ions, as I said last week. So, in all intents and purposes, you would have sodium ions and lead ions on the cation sites and chlorine on the anion sites, but the ratio of the number of cation to cation sites clearly changes as you change the... So this is the Temkin model. The ratio of the sites is no longer 1:1, it's a little bit greater than 1:1. Locally, however, everything's fine. If you, however, put it into the solid, then the ratio has to remain 1:1. Okay, so if you put in a sodium and a lead, okay, the lead 2+ has to form a vacancy on the cation sites. Every time you add a lead, and you add a vacancy. You have the chlorine here. The lead replaces two sodiums. One lead replaces two sodiums and creates vacancies. Negative ions stay put. The sodium ions are here. You replace one sodium ion by one lead ion and create a vacancy. The number of vacancies is equal to the number of leads. Now, as you get more and more concentrated in lead, the vacancies and the leads tend to associate to form pairs, and that just makes things more complicated, but you could still represent it this way. But it's no longer an ideal mixture of these. These tend to be forming pairs. A liquid solution with 75% iron and 25% sulfur. So this is a mat. Well, it contains iron ions and sulfur ions, contains FeS molecules. What's it contain? What kind of a model would you use to represent such a solution? Well, I would represent it as iron and sulfur on the same sublattice. Okay, but would it be an ideal solution, or
But what I was looking for here was the short-range order. Is it going to be highly short-ranged order? Or?
Okay, the one I was after is a one sublattice quasi-chemical model.
So everything's just on one sublattice, iron and sulfur on the same sublattice, but your iron-iron pairs plus your sulfur-sulfur pairs form FeS pairs. The omega would be very negative for that, so the iron and sulfur tend to form pairs because iron and sulfur are very different electronegativities. One's a metal, one's a nonmetal. If this is your iron sulfur going across the liquid system, the mole fraction of sulfur, here we have 50% FeS. They're miscible, but the heat of mixing is going to look very negative like this. Okay, because here at FeS, you've got mainly FeS nearest neighbors. It's FeS, FeS, FeS. It's a one sublattice model, but with a large amount of negative short-range ordering, and your entropy of mixing is going to look like that. Well, actually over here it's because you have other problems on this side, but certainly on this side it starts to look like that. To get over here, then it becomes more complicated because pure sulfur liquid is more okay, but at least up to say here you can treat it this way. Okay, so it's a typical mat. You would treat it as a one sublattice model of iron and sulfur, but with a large amount of short-range ordering, meaning the iron and sulfur tend to form nearest neighbor pairs very strongly. So I mean, pure FeS, pure liquid FeS is almost entirely, first nearest neighbors would be 99% iron sulfur. Very unlikely you're going to have two irons or two sulfurs next to each other because of the charge separation. The charge tends to localize on the sulfur to form sulfur ions. And although liquid FeS does, there are enough delocalized electrons that it still remains an electronic conductor. It's not all, it's not pure. You could treat it as Fe2 plus S2 minus, but not all the electrons tend to be localized. There tend to be some that are loose and are forming an electron cloud which can conduct electricity. Oxygen dissolved in liquid iron, interstitially. Yes or no? No. Well, first of all, oxygen doesn't dissolve in solid iron interstitially. It's too big. Secondly, you can't really talk about an interstitial in a liquid anyway, can you? But what I'm after is it dissolves as oxygen 2 or O? Monatomic or diatomic? It's monatomic. Okay. O2, oxygen dissolved in water is O2. Or else all your fish would die. But oxygen dissolved in the metal dissociates to form 80% MgCl2 and 20% KCl. Okay, you can't treat that as a, now if that was rich in KCl, you could make a very simple model with MgCl4 complexes, but you certainly can't because you're at the other end over here. Okay, so the only way to really treat that with the proper model, as I said last week, is you would use the quasi-chemical model on the second sublattice. So you basically would have it magnesium and potassium on one sublattice and chlorine on the other. But between the magnesium and calcium and potassium on its own sublattice, you would have a very strong, the magnesium, second nearest neighbor, plus potassium, second nearest neighbor, give to magnesium, potassium, second nearest neighbors. You would have a very negative short-range ordering parameter. You treat it as on the sublattice. So this is your mixing sublattice. You can ignore the chlorine sublattice, and you treat it by a simple one sublattice quasi-chemical model with a large degree of short-range ordering. Okay, so the tendency is for magnesium to have potassium in the second coordination shell, vice versa. Which, as I said, on the other side, on the potassium chloride side, is equivalent to talking about complex ions. Okay, if you have a magnesium ion, then it's got chlorine in the first coordination shell. And if in the second coordination shell it has mainly potassium. So here's your magnesium, first coordination shell is chlorine, second coordination shell is potassium, which means then that you favor magnesium, potassium, second nearest neighbors are favored. That then is equivalent to, almost equivalent to, talking about MgCl4 anions, complexes. We do not explicitly talk about, if you treat this thing with this system with a one sublattice quasi-chemical model, you are not explicitly talking about complex ions, but you end up with something that's mathematically about the same thing. When you then get on the other side, though, when you have more magnesium than potassium, then you really can't any longer talk about complex ions, because then you necessarily have to have magnesium in this shell because you don't have enough potassium. And then if you have magnesium second nearest neighbors, well then the complexes start to overlap, I guess. You can't really talk about complex ions. This magnesium over here has 4 chlorines around it, and this magnesium has 4 chlorines around it, but this chlorine is shared. So you're not really talking about discrete complex ions anymore. So the best way to treat it is simply like this. Which is the best way to treat it anyway, because now you have more parameters, you can do your curve fitting, it's better. But conceptually, if you're way over on the potassium side, conceptually you can talk about complex ions. On the other side, it's conceptually a little bit. Come on. B, silver bromide. Well, it's silver on the silver lattice, bromine on the bromine lattice, but you have excess silver. So the excess silver would go into the interstitial. The majority defects are silver, interstitial silver, and bromine vacancies. You have interstitial silvers, you have bromine vacancies. As you go to one side or the other. That you're exactly 50-50, you have an equal number of bromine vacancies and silver interstitials. As you go to one side or the other, you start to shift.
Excuse me, RJ, you said if the magnesium chloride amount was less, you could talk about the complex ion, discrete complex ions.
Number J?
The last one, yes.
Yeah, well, you're talking here, the model we can use for the whole concentration range is this model here. Oh yeah, you weren't here last week.
Sorry?
You weren't here when I talked about this, right? Okay, so in general, this is your best way to do it. But let's say you're very rich in potassium chloride. Okay, so if you're very rich in potassium chloride, okay, here's the thing, is that if you treat this system using this quasi-chemical model, in which you simply say that it's the second nearest neighbor, magnesium, potassium pairs, which are favored, then you can get a good representation of the heat and the entropy and so on. But we also know in these systems in which you have a very large amount of alkali chloride, you can also get a pretty good representation by talking about a complex ion model. Okay, so here I'm treating it by the short-range ordering model, I'm treating it this way, but I'm saying there's a strong tendency to short-range ordering on this sublattice. In the complex ion model, I'm saying there's magnesium here, and on the other lattice you've got chlorine and MgCl4. Clearly you can only use this in regions that are rich in potassium, potassium here. Otherwise you don't have enough chlorines to form your complex. But they say, well, but this model and this model seem very different. Conceptually, how can you show that these models are the same? All right, so what does this model mean, an MgCl4? It means you got a magnesium, well, what does the short-range ordering model means you got a magnesium here, and your second coordination shell you've got, of course, obviously chlorines, and then in the next shell around that, you've got a bunch of potassium ions. So your second nearest neighbors are magnesium, potassium, and they're favored, otherwise you could have magnesiums around it. But now if imagine this situation in a system that's very rich in potassium, this MgCl4 then could be considered to be a complex anion unit. And if you then treated this as a separate entity and mixing on an anion lattice with the chlorines, you can work out the mathematics, you get almost the same model. And this is even observed. People say, well, you use this when you're using the quasi-chemical model, we're talking about this, but I mean, people look, they do Raman spectra of these things, or UV spectra, and they see vibrational spectra that kind of, in these potassium chloride rich solutions, that more or less are what you would expect for an MgCl4 complex anion. So therefore we have complex anions, and therefore the quasi-chemical model doesn't agree with reality. But I say yes it does, because the complex in the quasi-chemical model, you're saying you got magnesium, the 4 chlorines, because of your ratio 2 to 1 of the Zs, potassium's in the next shell, so clearly this unit here is going to vibrate like an MgCl4 unit. Now, if you get rich in magnesium, of course, then you can't really do it, because now you start getting, you'd have to necessarily have magnesium. You must have magnesium-magnesium pairs, because there's not enough potassium, and then where this chlorine then belongs to both pairs, and both complex ions and things start. And that, when you start talking about complex ion sharing pairs, sharing a chlorine, then it's, now you can go a little bit further. If you want to consider a complex ion sharing a pair, well, then you can talk about a dimer if you like. Here, this is an MgCl4, and here's another MgCl4. So you've got an Mg2Cl7, and that's your dimer. And people start talking about dimerization. But after you start getting trimerization and so on, it starts to get a little bit. Okay, so you see how the complex model, the dimerization, the propensity for second nearest neighbor pairs. Okay, but this is then really, once you start getting into more concentrated solutions, the short-range ordering model becomes simpler mathematically than starting to try to mix your dimers and your trimers and your tetramers. And besides, if you get more than a dimer anyway, you can't really, if you have something like Mg3Cl10, that's not going to substitute on one lattice with a little tiny chlorine. So it starts to get a bit screwy.
Okay. The last thing here was this it's 1999 exam, wasn't it? Yeah. Okay, so it numbers 4 and 5 from the 99 exam. Okay, this is your log PO2 composition diagram for the iron nickel oxide and oxygen system. You sketched in the figure, which isn't here, but it doesn't matter. The log PO2, you got an iron nickel oxygen system. In the spinel phase, the two components Fe3O4 and NiFe2O4 are both inverse spinels. Develop a model giving the activities of both of them as functions of the overall composition in that solution. And I said you don't have to use the compound energy model, let's just look at even a simpler model. And we can do number B when the 3 phases, spinel, monoxide solution, and metal alloy are at equilibrium. Calculate the compositions of the 3 phases. The picture isn't there. I do have the picture. Yeah, there's your iron nickel oxygen diagram. That's the one that should be in the okay, this is your iron on this side, nickel on that side, and this is log PO2 at a constant temperature. And over here, you see you have the Spinel solid solution. The Spinel solution goes from Fe3O4 over to NiF. So this ends at 1/3, which is NiFe2O4. Okay, so you've got a solid solution here. Okay, your Spinel solution goes from Fe3O4 over to NiFe2O4. Now your Spinel solid solution extends 1/3 of the way over. This would be Ni3O4 over on that side, but you don't get all the way there. Why? Fe3O4 is a Spinel, Fe2 plus, Fe3 plus, Fe2 plus O4, an inverse Spinel, and NiFe2, sorry, how did I say it's a normal or an inverse Spinel? What was it? Both inverse spinels. Okay. So Fe3O4 is an inverse spinel. So it's Fe3O4, Fe3, Fe2O4. It's not quite exactly, it tends to be more mixed, but we'll assume it's a pure inverse spinel. Okay, and the Fe2O4 is also an inverse spinel, Fe3 plus, Ni2 plus, Fe3 plus O4. Okay. Now the reason this only goes over to 33%, the reason it's only soluble up to here is because the nickel 3 plus is not stable. So if you went it any further, you'd have to start to introduce some nickel 3 plus. And you can't do that. So and this is your solubility limit. So it's a solution of this and this. You can see it's obviously a one sublattice model because you have iron 3 plus on the two from this site here. And on the other site you have iron 3 plus mixing with nickel 2 plus and iron 2 plus. They're simply mixing on the second sublattice. And the equilibrium I wanted in the second case was this equilibrium, this invariant here, in which at a certain log PO2 at this temperature you have a spinel at this composition in equilibrium with this your monoxide solution, FeONiO, in equilibrium with the metal that's going to be almost pure nickel. So you've got your metal, which is almost pure nickel, VCC, in equilibrium with the monoxide containing about 40% NiO, 60% FeO, in equilibrium with the spinel at about 18% or something. Okay. So if we went back to the answers then, I could simply, as I said here, represent the thing this way, Fe3 plus here. On this lattice site you also have Fe3 plus, and then the Fe2 plus and the nickel. Fe2 plus and the nickel 2 plus are mixed in the ratio. I wrote 1 minus 3 and 3 so that the sum of everything was 2 sites on that lattice. And why did I write 3x? Because x is going to be the mole fraction of NiFe2O4 in this overall system. If you want, x then is x was the x-axis in that phase diagram. Okay, when x is equal to 1/3, when x equals to 1/3, you've got f, this is equal to 0. But when right in here, this is your binary system, your real binary system. This is x is 0, and over here you have x is 1/3. When x is 1/3, x was the axis in the phase diagram, which goes to, when x is 1, you would have Ni3O4, which is, so that's why I wrote it this way. You don't have to write it this way, I was trying to. Okay. So what is the activity of Fe3O4? The activity of Fe3O4 then is the mole fraction of iron 2 plus. Fe3O4 has iron 2 plus and iron 3 plus over here. So it's the mole fraction of iron 2 plus on the B sites times the mole fraction of iron 3 plus on the B sites. But once again, you want the activity of Fe3O4 to be 0 when x equals 0. So you have to, as we did in the first problem this morning, so in the denominator you have to put in the values of these when x equals to 0. So they're equal to the product of those two when x equals 0. Okay, so the mole fraction of Fe2 plus on the B sites is 1 minus 3x over 2.
because there are two sites. The nickel of iron 3 plus is 1/2. When X equals 0, it's a half. Okay, so the activity of Fe3O4 is 1 minus 3X. The activity of NiFe2O4 is the mole fraction of iron 3 plus on the B times the mole fraction of nickel 2 plus on the B, divided by the values of those two when X equals 1/3, when you're at the pure material, which again is 1/2. So that's equal to 3X. Okay, so the activity of Fe3O4 going from X to 1/3, the activity of FeO3O4 is 1 minus 3X. The activity of this stuff is 3X. It's basically just an ideal mixture on this site.
And that's what you get if you have an ideal mixture. I don't even know if this is just... okay, to define those compositions there, you got to consider the data. You got the mole fraction of... this would be, so the nickel plus oxygen is NiO. You remember now you have the three phases, the metal phase, the monoxide phase, and the spinel phase. This would indicate, so this monoxide phase, we assume that its activity is equal to its mole fraction. We're assuming the activity of the nickel phase is equal to its mole fraction. Same thing here, but in the spinel phase, we're assuming, so the activity, equilibrium constant of this, it's the ratio of the activities. I'm assuming ideal solutions. So, but in the ideal spinel solution, the activity of Fe3O4 is 1 minus 3X. The activity of iron in the iron solution is just 1 minus, assuming all the solutions are ideal. So, for this equilibrium, this is the ratio of activity of nickel oxide in the monoxide solution, which I'm assuming is equal to the mole fraction because it's an ideal solution. This is equal to the activity of nickel in the metal solution, which I'm assuming is equal to X nickel because it's an ideal solution in this rough approximation. The FeO, actually I put in a gamma, not FeO there, because there was data given for the Fe3O4. I'm putting in the ideal activity and so on. We simply solve the equations. It's just, I don't think we really have to worry. The whole point here was simply that when you're talking about an ideal activity of Fe3O4, you've got to use what you used here with the proper model. And the final one was one more. Oh, Jesus, these have to keep coming up. Okay, ferro pseudo-brookite. Again, okay, last ceramic. FeTi2O5. It's a ceramic. This is quite a common thing with two cation sublattices. Okay, so Fe2 plus is on the A and titanium 4 plus is on the B. The ceramic Ti3O5 has the same structure and is represented as Ti3 plus on the A sites and a mixture of 3 plus and 4 plus on the B sites. That's the same crystal structure as ferro pseudobrookite. Solid solutions then can be represented this way, with the ions mixing randomly on each sublattice. Play around with the quasi-chemical, with the sublattice model. Okay, so this is how you would do the sublattice model, ignoring the oxygen lattice. Here you have Fe2 plus. Okay, here you would have Fe2 plus with both Ti4 on this lattice. Here you would have Fi2 plus with Ti3 on this lattice. Two Ti4s on this lattice. Here's Fi with two Ti3s on this lattice. Here you would have titanium on this lattice with the titanium 4s, titanium 3 on this lattice with the titanium 3s for your four. Okay, for your four end members. Okay, the solution here is iron 2 plus, titanium 3 plus on that lattice, and titanium 4, titanium 3 on that lattice. With two sites on this lattice, one side of this lattice, two sites on this lattice. Okay, so the end members then are, these are the end members then, 2 plus and 3 plus on that lattice, and 4 plus, 3 plus on that lattice. This is neutral. These are all hypothetical charged compounds. This is your neutral line, and at the end of this neutral line is Ti3O5, which has titanium 3 plus here and a mixture of titanium 4 and titanium 3. So Ti3O5 is titanium 3 plus, titanium 4, titanium 3. So it's this halfway in between. And that's your neutral line, which is your real
binary system between ferroceribrokite and Ti305. So all real solutions then necessarily lie on this line because that's the only neutral line. But where on this line? Where on this line is the point on the line that will give you the,
Well, depends on the overall composition. Okay, so we have X going this way and Y going this way. And
along the neutral line, actually I wrote the thing this way. If I wrote in the ferroceribrokite 1 minus X, well this X is Y is X over 2.
Y is X over 2. We've done a lot of that before. X is the ratio of the A sites, and Y is the ratio of the B sites, and along this line, Y is equal to X over 2. Forget what I said. Okay, so we substitute the thing this way. We make 2 mixing on that site, 1 mixing on that site. Standard fair.
But again, it's the fact now that G naught of Ti305, of real Ti305, okay, this G naught here, this is the Gibbs energy of FeTi204. The Gibbs energy of Ti305, which is a real compound, is going to be the Gibbs energy of this, plus the Gibbs energy of this divided by 2, plus the configurational entropy term for mixing on that sublattice. Okay, Ti3, real Ti305 is equal to Ti3 plus, Ti3 plus, Ti4 plus. Okay. So real Ti305 is at this point, so it's a mixture of this Gibbs energy plus this Gibbs energy divided by 2, plus a mixing term for the Ti3 and the Ti4, which mix randomly on that sublattice.
Okay, so
The Gibbs energy of that end member is the real FeTi205. The Gibbs energy of real Ti305 is 1/2 this Gibbs energy, plus 1/2 this Gibbs energy, plus the Gibbs energy of mixing on that second sublattice. This leaves 2 Gibbs energies to fix. You can choose one arbitrarily. The model parameter is basically delta G exchange for the 4 sets. This here only fixes the sum of these two. Your delta G exchange, which is going to basically decide how much these things, whether they want to mix or not, is going to be your model parameter. Okay, so this here fixes this Gibbs energy. This fixes the sum of these two. This fixes this plus this minus this minus this. So you got 3 things fixed. You got 4 things, so one of them can be chosen arbitrarily. This then, your delta G exchange is going to determine whether these things really want to mix or not along that line. Your delta G exchange then, which is this plus this minus this plus this, is going to determine whether this forms an ideal solution, a negative deviation, a positive deviation.
okay. So much for the compound energy formalism. Any questions about these things? All right, I want to continue with the molten, with the slags and things. Maybe we could take a break though first. Okay, this was number 49, these slags and things, but let's take a 10-minute break. And, so we can turn this off then.